Okay. All right, just a quick note before we start, ladies and gentlemen. Okay, quick note. You've had your extra credit for question number 7 from chapter 5, the study question. You'll find the key under week 2. So if you're interested to see if your answer was correct or close to correct, you can check it over here. I also put couple of YouTube videos. Next week is going to be HPLC and GC. I will give a brief overview on Friday on what you're going to do, but the actual lectures on HPLC and GC start next week. So coming into the lab, it would be great. We will, if we have time on Friday, I'll show the YouTube videos in class and give you an overview of what you're going to do. If we don't have time for the YouTube videos, I'll just give you an overview, and I would like you to look at these before lab next week, okay? Okay, with that, we can start with our regular recap questions. Okay. What is supercritical fluid chromatography? Let's see, Bailey. How do you make carbon dioxide liquid? Farah, you had your hand up. Do you know? And pressure. Yes, that is correct. And then when you have that, what were you going to add to that? Were you going to add anything to that? How does it differ from regular HPLC and GC, Jeshu? We can add methanol to it. Yeah. Yeah, it will become slightly more polar, and that will be helpful for what? Well, yes and no. You're combining a couple of things here. Yes, adding methanol will make it be more applicable for a little bit relatively polar compounds. If you just have CO2 as fluid, it will be mostly for nonpolar compound. So mixing methanol, it makes it more viable for applications that have compounds that are not slightly more polar. And also, it is a very diffusive, I'm not going to say that word. I want to use a different word for it. Viscosity is low. That makes the partition of solutes between the mobile phase and the stationary phase faster, so you have better resolution, separation that is, and shorter analysis time. And also you can use columns similar to what you use in HPLC, and you use detectors similar to those that you would use for GC. All right. What is reverse phase chromatography, Sven? Do not read. Yeah. Polar solvent as mobile phase, you said? Okay, yes. And nonpolar as stationary. And which compound will elute faster, nonpolar or polar, Ben? Polar will elute faster. Very good. In reverse phase paper chromatography, yeah, we did say that, kind of. The polar will move more with the mobile phase. What does TLC stand for, Claire? Wrong. Tender love and care. Thin layer chromatography. I put that in there just to say no to the first person that would answer. Sorry, Claire, it had to be you. Okay, how does TLC differ from paper chromatography? Yes, Christina? Huh? It has better resolution. It's faster because of that thin layer of a material, mostly silica, that you would put, and it's more regular, evenly distributed, smaller particle size compared to paper. So it's more efficient than paper chromatography. What's the difference between isocratic and gradient? You go ahead, Yonji.
Yeah, isocratic, you have only one mobile phase, or
So isocratic what? What did you say?
one mobile phase.
Okay, or mobile phase that does not change over time.
Okay, and then
The gradient.
has like various mobile phases.
So various mobile phases that you would mix them to end up with a mobile, various solvents that you would mix to get a mobile phase that changes over time. Okay? And what does increasing the strength of the mobile phase mean? Go ahead.
It means you increase basically you adjust it to increase the affinity of the solute to the mobile phase so it goes through.
Perfect. So you put something in the mobile phase, you change the characteristic of the mobile phase to make the solute leave the stationary phase and move along with the mobile phase faster. It will move along eventually, but you will make it move along faster and have more interactions with the mobile phase and less interaction with the column. Okay, so we can, with these in mind, we can move ahead and talk about the different separation modes using liquid chromatography. So we introduced it a little bit before, a couple of times. Adsorption chromatography is by its name, the solute adsorb to your column, to your stationary phase basically. It adsorbs via different interactions. It could be van der Waal, electrostatic, hydrogen, hydrophobic interactions. All these types of interactions can take place with the solute. This is your solute, and this is the functional group that you would have on your stationary phase. Yes, Ben?
So if you have the electrostatic force there, how come that's different from ion exchange?
Okay, so electrostatic interaction does not have to be necessarily when you have an ionized form. You can form electrostatic interaction because electrons usually are, they move around. You don't have to have always a charge associated. The electrons that are shared within a molecule can actually move around, and you can have electrostatic interaction that way.
Less specific?
Good question. Would it be less specific? Well, ion exchange is not really a specific interaction. You have a positive charge interacting with a negative charge, basically. And so it is not a specific like would be an affinity chromatography specific. Okay? So you might have charged groups and you may not have charged groups that are being separated and interacting via electrostatic interaction. But that's a very good and smart question. Thank you. Okay. Adsorption coefficient is not constant. So in partition chromatography, partition coefficient is constant. You can reach a constant one at equilibrium. But in adsorption chromatography, it's really concentration dependent because there are, on a given stationary phase, there is a constant number of functional groups. And therefore, there is a specific binding sites. If you overload, if you inject a sample or if you add to your column a sample that has more solutes than the amount of functional groups, they will not interact, and you will have poor resolution and poor separation. You don't want to do that. That's why there's always, based on your column dimension, based on your functional groups on the stationary phase, there's always a range of how much sample you can inject. So absorption coefficient is really dependent, is a concentration dependent, and it depends on how many functional group you have in your stationary phase. Okay, So adsorption chromatography, you have basically your stationary phase is a solid, and it could be silica, alumina, or charcoal, or it could be a bonded silica, for example, bonded with a hydrophobic group or bonded with an ionic group. The elution order of solutes depends on their relative polarity. So if we're just using solid silica, for example, or alumina or charcoal, it depends on how polar or non-polar your solute is. So if it's charcoal, that would be non-polar. So the more non-polar your solute is, the more it's going to interact with the charcoal. And it requires more time to elute. And you need to increase the strength of your mobile phase for it to leave. And the opposite is true for silica and alumina, that these are more polar surfaces. Okay. So solute and solvent usually compete for active sites on the stationary phase. So for example, if you have charcoal and you're eluting with water and let's say 10% acetonitrile, your non-hydrophobic components are going to have lots of room to interact with your column. Changing the concentration of acetonitrile in your mobile phase, acetonitrile is a nonpolar organic solvent. When you increase the acetonitrile in your mobile phase, then your acetonitrile will start interacting with your nonpolar surface. And then your solute will like to interact with the mobile phase more, and then will leave the column. Changing the strength of the mobile phase will alter solute stationary phase interaction, and that we talked about that. Increasing the strength of your mobile phase will allow your solute to interact more with the mobile phase rather than the stationary phase. So your stationary phases can be bonded. Silica, for example, is commonly bonded to C8, C18, or even C30. By C8 and C18, it's a chain of hydrocarbons, basically. The longer the chain, the more hydrophobic it is. So C18 is a very common one that we use, but if you want to, let's say, separate carotenoids, like Amy does, she uses a C30 column, right? Okay. So silica has OH groups, and the OH groups are derivatized, or at least are chemically bonded to your C8 or C18 or C30. Questions on adsorption chromatography?
So the longer chains of hydrocarbons have what effect?
The longer chain of carbon and hydrogen, then they become more hydrophobic. Yep. So I want to go back to Ben's question. It's just haunting me a little bit. Adsorption chromatography can be general, where all of these different interactions occur, and it can be specific. So affinity is an adsorptive chromatography. Ion exchange is an adsorptive chromatography. And hydrophobic interaction chromatography is a type of adsorptive chromatography. Different stationary phase and different levels of specificity. Okay, so this would be the most accurate answer to your question. Okay. Partition chromatography. We talked about that, and it is when your stationary phase and mobile phase are both liquid. And you do have a constant partition coefficient in this case. At each equilibrium, you will have a constant value where you have a set concentration in the mobile phase and set concentration in the stationary phase. And Jenny is being disruptive. That's okay. That's a tiny phone.
Yeah, my ancient flip phone, yes.
Okay. Lost my train of thought. So you do have, like I said, the solutes partition between the two liquid phases. And then again, elution, that means the movement and the departure of the solutes from your column is dependent on nature of the phases, what you have in combination of mobile phases. When you combine solvents to have a particular mobile phase of a specific polarity, you can change that. You can start your mobile phase as, like I said, 10% acetonitrile, 90% water, or you can start as 30% acetonitrile, 90% water, or you can have a non-polar starting mobile phase with mixing solvents in, and you mix depending on what solutes you have and how close of partition coefficient they have. I will give you examples later when we start talking about HPLC. I'll give you more concrete examples. And when you are also changing the pH can affect how solutes interact with the different phases as well. And this we talked about before, the difference between normal and reverse. You already know that. What normal is, you have a polar stationary phase and a non-polar mobile phase, and the opposite is for reverse. So for partition chromatography, again, you have a support, and that support is impregnated with a liquid, with a fluid. Silica gel, it will be probably hydrated silica, so the moisture on your silica or the water on the silica is your mobile phase. Same with cellulose and glass beads. You can also impregnate with liquid or mostly polar liquids. Sometimes your liquid phase is actually covalently bonded to a support via chemical reaction. That would be bonded support. And bonded support can also be, like I said earlier, for solid stationary phases as well, not just for liquid. So you have bonded support whether your stationary phase is liquid or solid. You don't have these slides in your packet, but they are in the updated PDF version on Moodle. I added this section because this is part of the new chapter, revised chapter that will be in the new book. So hydrophobic interaction chromatography is a very common chromatography that is also a subset of adsorptive chromatography because you have a solid phase, stationary phase, and a liquid mobile phase. In this case, interactions are very specific. They're hydrophobic interactions. Okay, and they are weak in nature. So the hydrophobic phase that you choose is a weak hydrophobic stationary phase so that you don't have very strong interactions. You do not want to have a strong interaction. Otherwise, it would be very hard to have them leave the column. And second, you will cause denaturation, whether it's mainly used for protein separation. So if you use really strong hydrophobic interaction, then your protein will denature. So it's adsorptive chromatography, so the biomolecules will adsorb to a weak hydrophobic surface at a high salt concentration. And like I said, it's mostly used for proteins and enzymes. Enzymes are proteins, antibodies are proteins. So these are mostly the solutes that we use this kind of chromatography to separate and isolate. And because the nature of these compounds, they are charged. In order for them to interact with the column, you mask the charges. And I'll show you a figure in a bit here. So the stationary phase usually use a hydrophilic support, such as saccharose is an agarose gel. So agarose is a hydrophilic support, and bonded to a hydrophobic ligand, such as butyl. So you have butyl saccharose is a common one. So the hydrophobic ligand, like I said, are not really strong hydrophobic groups, but they are hydrophobic enough to attract interactions with the biomolecules. The mobile phase, you commonly start with a high concentration of salt, and then in order to elute your samples or your solutes, you decrease salt concentration down to 0 molar. You can do that in a gradient way where you gradually decrease the salt so you get separation. Or if you don't care about separating, you just want to collect every single protein in your sample, for example, you switch from 1 molar to to 0 right away, and then all your protein will come out as one peak. If you want separation, then you can gradually decrease the salt, and you get separation that way based on the charges or differences in the charges. Here's an illustration. So you have your hydrophobic surfaces, and you have the molecules with hydrophobic regions. And then when you have high salt, you you enhance hydrophobic interactions actually, because you are shielding the charges. And then the most hydrophobic component will interact the most, and the least will interact the least and will move faster down your column. So the least hydrophobic will elute first, and the most hydrophobic will elute last. And again, to encourage this to leave the column, you reduce the salt concentration. So this technique is mostly used, like I said, for proteins. Enzymes is a subset. Antigen separation, using, well, antibodies, and what else I said? Enzymes. Yeah. Okay. Obviously. What is it? Yeah, it's just for fun, right? Hydrophobic. Okay. Ion exchange chromatography is another form of adsorption chromatography. It's a very specific form that, by its name, what you're separating are ions. So they can be small ions, they can be big ions, as long as they carry charge. So any compound, molecule carrying charge can be separated and isolated via ion exchange. So the interaction is mostly governed by electrostatic interaction. So you would have a charge on your stationary phase, and the ion with the opposite charge will interact with it. So your stationary phase is basically a cross-linked resin or polyelectrolyte. So it's a resin that is a lot of cross-linking and has functional groups, and these functional groups have charge on them. If they are highly cross-linked, you will have very small pore size, you have a lot of surface area, you have a lot of functional groups, but if they are highly cross-linked, you will use them only for small molecules, sugars or amino acid separation. However, if you want to separate larger molecules, such as proteins, for example, that are charged, then you want to use a matrix that is lightly cross-linked, so you have larger pore size for the protein to get into and interact with the functional groups. So a polystyrene polymer is very highly cross-linked. So it is mostly used for small molecular weight compounds. And then there is an R group here in the chain. So this R group can be derivatized to carry a positive charge or a negative charge. So when it carries a positive charge, and this is where confusions start. When it carries a positive charge, it becomes an anion exchanger. When it carries a negative charge, it's a cation exchanger. Why is this confusing? Huh. Yes. So it's exchanging. What is exchanging is your solute is exchanging between the mobile phase and the stationary phase. So whatever the charge of your solute would be the name of your chromatography. So if your solute is an anion, is negatively charged, so it's an anion exchanger. It's exchanging an anion. So in order to exchange an anion, it should be positive. In order to exchange a cation, a positive charge, it needs to be negatively charged. Okay? So keep in mind that the name of the chromatography implies the charge of the solute, not the charge of the stationary phase. Okay. Polysaccharides based, which is a chain of glucose units, and it would be, the OH groups would be derivatized. In this case, it's loosely cross-linked, so it is for large polymers. And again, the OH group can be derivatized to carry a weak base, weak acid. Again, this is another confusion for students. When we say a weak acid, it's carrying a negative charge. Weak acid or strong acid, they carry a negative charge. Why? Because acids have tendency to donate what? Protons. So when they donate a proton, they become negatively charged. Bases, on the other hand, accept protons, so they are positively charged. So when you have an acid group, it would be what? An anion exchanger or a cation exchanger? What? Who's going to be the brave soul? Sven. No, John. What's that? What was my question? Okay, it was the weak acid is a cation exchanger. You're correct. Okay, so the weak acid, it will carry a negative charge, therefore it is a cation exchanger. Even the strong intermediate or strong acid are also cation exchangers, and the weak base or strong base are anion exchangers. And then I'll tell you a little bit more about the difference between weak and strong. So you're going to learn about something called selectivity and capacity of the column when we talk about resolution. But just briefly here, selectivity is how selective or specific a certain exchanger is to the solutes that you are trying to separate. So you can affect selectivity by different parameters. Okay, so first of all, if you have, let me see if I have it on the next, do I have it? No, I don't have an illustration. Let me then draw an illustration. Do you know what ionic valence is? What is an ionic valence in simple terms? What is an ionic valence? Yes, Anne.
Is it basically it's the molecule formed when the positive and negative molecules go together, like NaCl, they create a
Pretty close. Agnes? No, this is too specific for me. Okay, ionic valence is how much charge density does your molecule carry. Okay, so you have charges that a molecule is carrying. I'm going to simplify it. So you have here, let's say, 4. The net positive charge is 4. And then you have another one with a net positive charge of 2. And then you have one with 1 charge. And then you have your stationary phase with your functional groups. Okay? And then your functional groups are going to be, there will be quite a few of them. And since we are doing cation exchange, then you have negatively charged functional groups all over. Okay, so there are many of them. Which one of these three, A, B, C, will elute first or leave the column first? Yeah, because the more positive charge you have, they're going to interact more with your functional groups. And the less you have, they're going to interact less. So they're going to move faster. Okay? So the retention will be less on the column. So that's the valence effect. The radius effect also have an effect because it depends on the pore size. If it's a large molecule versus a smaller molecule, there might be some kind of hindrance. And of course, the concentration, how much of that you have versus this versus that. So you can actually change the selectivity of your column by changing the pH. If you change the pH, you might reduce the number of the negative charge groups. Or you might increase the number of the negative charge groups. You want to remember something, and this is specific for weak cation or anion. So if I go back to here, this is a negatively charged weak acid. If I reduce the pH of my mobile phase, what will happen to this? Okay, so well, then it will pick up a proton. Then you will lose a negative charge. Okay? If you increase the pH, most of your groups will be ionized. So you can change how strong or weak your interaction is going to be with your solute based on changing the pH of your mobile phase if you're working with a weak acid or a weak base. pH affects selectivity, yes, Ben. Definitely, you are ahead of the game. I was going to talk about that, but you are ahead of the game. Yes, but each like this, the way it ionizes or deionizes is different at a particular pH. There is range that is different probably from the pH that your solute is going to be fully ionized or non-ionized. Changing the pH, yes, will affect the ionization of your stationary phase and will affect the ion status of your solute as well. And that plays a role when you're actually, I told you you're ahead of the game, but I'm going to say it anyway. When you want to elute your sample, let's say you have a cation exchange. So it's a positively charged solute, right? You want it to leave your column. How would you change the pH to make it not interact with the column? How do you change the characteristic of your solute so that it's no longer interacting with the column? It's positive. So you increase the pH, then it will give up its proton. It's giving up its proton, it loses its charge. So it's no longer interacting with the column. Of course. And changing the pH is one way of eluting your sample. So when you have a strong base or a strong acid, it remains positively charged or negatively charged at a wide range of pH. Between 2 to 10 it carries, no matter how you change the pH, it will not affect the charges of the column, but it will affect the charges of your solute specifically. It's a very complex chromatography and very specific to the different types of solutes. So, and the best way to figure out how to elute your sample is by trial and error. Just see what works better and what you know about your solute. And sometimes you don't know a lot because you might be dealing with unknowns. Okay. So like I said, the strong acid or strong base, they are not affected by changes of pH. However, weak acid and weak bases are affected by pH. And make note of this. When you have a weak acid or a weak base, and you want to separate samples that are very close in their ionic valence, then you want to use weak cation exchanger and weak anion, then you can play around with the selectivity. Then you can change the pH so that you have certain selectivity so that you can separate ions that are very closely related. If you have a really strong base or strong acid, you won't get separation of ions that are closely related in charge. Okay. So selectivity is affected by composition and pH, and by composition I mainly mean salt concentration. So salt concentration, the salt in your sample provides something we call counter ions. Okay? So the counter ions compete with your solute for interacting with the stationary phase. So if you have NaCl, for example, and you increase the salt concentration by using NaCl, so the sodium will interact with the negatively charged stationary phase, for instance, so your cations no longer have room to interact, so they leave the column. So increasing salt concentration in this case helps with elution from the column. So in ion exchange chromatography then, what's the most, yeah? Electrostatic, okay, that's cool. You'll notice I shifted things around. You can flip to affinity chromatography. I want to finish with all specific forms of adsorptive chromatography before moving to size exclusion. Affinity chromatography is another form of adsorptive chromatography. So now I introduce, this is the third specific form of adsorptive chromatography. In this case, it is, as I said last time, it's the lock and key theory here applies, because you have a very specific interaction, whether it is ionic or not, it's not covalent, ionic or hydrogen bonding or covalent, not covalent, hydrophobic or van der Waals. So it could be a combination of these different interactions that are very specific. So sometimes you use antibodies as your ligand here that would be used to specifically separate, let's say you want to separate a mixture of proteins, but you are really interested in one type of protein, so you use a specific antibody to separate it. So no matter what other proteins you have in your sample, you'll be able to capture that one. Sometimes if you are after separating enzymes from a mixture, again, you would use a very specific enzyme inhibitor to the enzyme mixture that you have, and then you would get your specific enzyme. Sometimes it's more general. Lectins is a group of proteins that have affinity to groups of glucose and mannose that could be glycoproteins that you're trying to separate, for example. So your lectins will interact very well with carbohydrate moiety. Okay, so basically you have a support that is inert, does not react with what you're trying to separate. You have a spacer arm, which could be like a carbon chain. And you have your ligand. The ligand could be a non-specific lectin, or it could be an inhibitor to an enzyme or an antibody. So there is a stage where we call activation of the column, where you carry out a certain procedure to make sure that your ligand binds to the spacer that is bound to the support. And then you run your sample and separation occurs. Okay? So it should be a high surface area material to enhance the capacity of your column. And then it's porous, does not absorb anything, and most commonly use agarose, cellulose, dextran, glass. So if you want, so your analyte or solute interacted with the ligand and you want to remove it from the column after you're separated from everything else. In order to do that, there is something called non-specific elution and biospecific elution. Non-specific, that means if you change pH or salt or temperature, you're going to change the way that solute is interacting with your ligand. You're changing the affinity, changing the charge, you're changing the ionic valence on the molecule itself, and also the temperature. For example, if it's an enzyme inhibitor and an enzyme, it requires a particular temperature to interact, then you encourage this interaction. Okay, so biospecific is when you add to your mobile phase the ligand you have on your stationary phase. So what you're doing is you're giving your solute another ligand in your mobile phase, so they would interact with that ligand and leave the column. Which one? Agnes? You don't want to say? Okay. You're just smiling. Come on. I said it when I started. No. 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 Agnes? No. No. All of the above. It could be any of these. It could be multiple, it could be one, could be two, could be all, depending on what you have in there. Okay. Size exclusion chromatography is a very unique type of chromatography. It does not involve physical interaction or chemical interaction. So here, it is purely based on the size of your molecule, not how it's going to interact physically with the stationary material. So many names are used for this kind of chromatography. So you might hear gel filtration, gel permeation, size exclusion. They all mean the same thing. It's separation based on size. And what happens here, you have a column that is packed with a very porous material, but very inert material. Does not really interact with your compound. So it's very porous in a sense that your molecule that you are, or the molecules you're interested to separate will either will be small enough to enter the pores, or will be large and will not enter the pores at all, or will be medium size where they are not accessible to all pores. So the pore sizes that you have on a particle could vary in their size. So you would have a range of molecular weight or size that you can actually separate. So those large ones that do not do not go through the pores, they travel with something we call void volume, which is the volume that is interstitial volume. That means the volume that is not, it's outside of the particles. I don't know if you can visualize it, but if you have like particles, your column is packed with particle. So the volume that of the whatever solvent you're using that goes through and not in each particle has pores, and the pores could be different size pores. Okay, so your volume that passes between the particles, not within, is your void volume. And the particles that are large do not go through any pores, will travel between the particles. And the small ones the smallest one, will enter all of the internal particle pores. So it will be delayed the most. Take its time, go in and out to every single pore, not literally, but can go potentially, and will be last to elute. So in this kind of chromatography, larger molecules will elute first, smaller molecule will take longer to leave the column. So this is another demonstration similar to what I drew here. You have your particles, different pore size. You have different particles depending on their size. Some are accessible to all pore sizes. Some are accessible to some pore sizes. Others do not really go through any. So a chromatogram, this is a very optimistic chromatogram with size exclusion. Usually you don't get that wonderful separation. But theoretically, you can separate based on differences in molecular weight or small differences in molecular weight. So this is your void volume. That means the volume of the anything that goes between the particles. And this is your total volume, because the total volume is the void volume plus the internal volume of the pore. So from here to here is the internal volume within the particles. And then from the beginning to end is your total volume. VE is your eluent. So if you're interested in this took this much volume to elute. That would be elution volume of that particular solute. To determine molecular weight, oftentimes size exclusion is used to determine the distribution of molecular weight in your sample. And sometimes it's just used to separate a mixture based on their molecular size distribution. But if you want to determine the molecular weight of your mixture or a compound in your mixture, you can actually generate a standard curve. So each column have a specific range depending on the pore sizes within your particles. So you can have a very broad range, you can have very narrow range depending on how big your pore sizes are. And then with it comes a suggested standard mix that you would use, and to generate this kind of a standard curve where you plot something called, again, available partition coefficient, which is the volume of your eluent minus void volume over total volume minus void volume. So you get the value and you plot it against the log of molecular weight. And then you get this, based on the different standards you have in the mixture, and then you get your unknown, you run it, you get the KAV of your unknown and try to figure out its molecular weight. What kind of interaction? Thank you. This handout that I gave you earlier, if you don't have it, please let me know. I'll make a copy. This is not, you cannot find it anywhere in your book because it's part of the new version of the chapter. But I gave you a handout. This is a great study guide for the different type of chromatography. The stationary phase, the mobile phase, how you increase the strength of your mobile phase, what compound elute first, and what type of interaction you have. Best study guide that you can ever find. Okay, I will continue with analysis of a chromatographic peak next Friday. Oh, this coming Friday.